Welcome everyone to our first video on quantitative equilibrium. In this video, we are going to start off by looking at the stoichiometry of equilibrium systems. And then we'll go through an example of how we can use that stoichiometry to calculate the equilibrium concentrations, even if we're not able to measure all of the species in an equilibrium system directly. So far, we've talked about how equilibrium systems change in predictable ways. Now, it's not that they just change in predictable ways. They change in predictable quantitative ways, in that we can figure out precise measurements of systems at equilibrium given a certain amount of initial information. The difference between equilibrium stoichiometry and regular quantitative stoichiometry when reactions go to completion is that for an equilibrium system, we don't necessarily know how much change is going to occur. Even though we don't know how much change is going to occur, one thing is the same in all chemical reactions, in that the chemical species change according to the ratios in a balanced chemical equation. The best way to understand how this works and the difference between a one-directional chemical reaction in an equilibrium system is to look at an example. So let's do that now. Here we have the equilibrium system in which there's, on the left-hand side, the reaction between hydrogen gas and fluorine gas. And on the right-hand side, we have hydrogen fluoride gas. In our example here, we are going to take a situation where we react 2 moles of hydrogen gas with 1.5 moles of fluorine gas, and we react them in a 1 liter container. We're going to let the system react and reach equilibrium. And what we're going to try to find out is the equilibrium concentrations of the hydrogen and hydrogen fluoride gas if we know that the equilibrium concentration of fluorine gas is 0.8 moles per liter. In this example, we are given the initial concentrations of all of the chemical species. We are also given one of the equilibrium concentrations as well. This will be enough for us to determine all of the other equilibrium concentrations. For most equilibrium problems, we are going to set something up called an ICE table. ICE stands for Initial Change Equilibrium, and it always refers to concentrations. Initial are the concentrations immediately before the reaction begins. Equilibrium, obviously the equilibrium concentrations when the system stops changing and reaches that steady state. And then the change is the difference between our starting point and where we end off at equilibrium. So let's flip over to the whiteboard and look at how we build an ICE table given the example that we just looked at. Here's the problem written again, and now I've created an ICE chart. The way we set up an ICE chart is along the top row, we have our balanced chemical equation. On the first column, I've labeled the concentrations, initial, change, and equilibrium, remembering that we're going to be using these square brackets here to represent concentration. Now let's fill in the ICE table with the information that's given in the equation. So the question tells us that we start off by reacting 2 moles of hydrogen and 1.5 moles of fluorine gas in a 1 liter container. Now, these values here are always concentration. So if we're given amounts, we need to convert those into concentrations. This is easy here because we have a 1 liter container. So the concentration initially of hydrogen gas is 2 moles per liter. Let's write that in now. For fluorine gas, it's 1.5 moles per liter. And there's no information about hydrogen fluoride. We will assume we're starting off with none. The other concentration that's given to us is the equilibrium concentration of fluorine. I'm going to leave that out for now because first I want to address the change. Chemical systems at equilibrium involve incomplete reactions, which means that Not all of the hydrogen and fluorine are going to be converted to hydrogen fluoride. We just don't know how much is going to be left over at the end. What we do know is that they are always going to react according to the balanced chemical equation. For every 1 mole of hydrogen which reacts, will react 1 mole of fluorine, and that'll produce 2 moles of hydrogen fluoride. We also know that this reaction is going to proceed from the left to the right because we're only starting off with chemicals on the left-hand side, so the only direction it can go is moving from the left to the right. The way we're going to address the change is going to let the change be equal to a variable x. Let's do that now. Now we know the hydrogen gas is going to decrease in concentration, so this change is also going to be negative. For every 1 mole per liter that hydrogen gas decreases in concentration, fluorine gas will decrease by the same amount because it's a 1-to-1 ratio on the left-hand side. For every 1 mole of hydrogen gas that reacts with 1 mole of fluorine gas, we are going to produce 2 moles of hydrogen fluoride. So the change in concentration of hydrogen fluoride is going to be equal to 2x. So let's note a few things about the change. For most problems, we do not know the extent of the change, so we will let it be some variable. The change is going to happen proportional to the coefficients in the balanced chemical equation. So you can see that the coefficients in my change match the coefficients in the balanced chemical equation. In many problems, we will know the direction of the change. Here, since we didn't start off with anything on the right-hand side, there's only one direction. The right-hand side is going to increase in concentration, and the left-hand side is going to decrease in concentration. The signs on the change have to be the same for everything on one side of the equation. If hydrogen gas is decreasing in concentration, fluorine gas is going to be decreasing, and the sign on the change on the opposite side has to be opposite. If the left-hand side is decreasing in concentration, the right-hand side must be increasing in concentration. The equilibrium concentration is equal to the concentration that we started with plus any change that occurred. So for hydrogen gas, we started with 2 moles per liter, and we decreased by x moles per liter. So I'm going to write that in 2 minus x. I'm going to leave out the units right now and just remembering that we're always dealing with moles per liter. Fluorine gas started with 1.5 moles per liter, and it's going to decrease by a concentration of x as well. We did not start with any hydrogen fluoride, and it's going to increase by 2x. So my equilibrium concentration, 0 plus 2x, or 2x. Now that I've filled in my ice table, I'm going to use the final piece of information here to solve for x. We're given in the question that the equilibrium concentration of fluorine gas is 0.8 moles per liter. We determined through the ice table that the equilibrium concentration of fluorine gas is equal to 1.5 minus x. Therefore, 1.5 minus x is equal to 0.8. X is equal to 0.7. A common problem in equilibrium questions is stopping when you've got that x value. Remember, x represents the change. So now we know how much these chemicals are going to change between their initial and equilibrium concentrations. But here we wanted to determine all of the equilibrium concentrations. So we know the fluorine concentration, And now let's use our value for x to determine the concentration of hydrogen gas and hydrogen fluoride. So the concentration of hydrogen gas at equilibrium is 1.30 moles per liter. The concentration of hydrogen fluoride gas at equilibrium is 1.4 moles per liter. Although equilibrium problems are going to get much more complex in terms of the math and some of the problem solving, the basic setup is always the same. We started off with a problem where we had a balanced chemical equation. We created an ice chart and we plugged in the information that we knew, and we used the variable x to represent the change, which is often an unknown. That change is always determined by the balanced chemical equation. We saw that the signs on the change always have to be opposite on one side of the equation and the other, because if one side of the equation is decreasing in concentration, the other has to be increasing. Once we filled in our ice table, we used the information that we had at hand, in this case, the equilibrium concentration of fluorine gas, to solve for our other unknowns.